Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is soft starters. Our objective is to introduce a solid-state power electronics device known as a soft starter. Soft starters reduce inrush current and modify acceleration and starting torque characteristics. This lecture operates under the assumption you've watched the primary resistor reduced voltage starters lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. As you are no doubt sick of me reminding you, the direct and instantaneous application of full voltage to a motor at standstill produces a tremendous surge of current known as inrush. Although brief, inrush current can place an unnecessarily high demand on the electrical distribution network, and industries often pay a financial penalty for such events. Additionally, the abrupt acceleration of a motor from standstill may damage the mechanical linkages like belts, chains, shafts, gears, and couplings the system uses to manipulate the applied load. It is for this reason reduced voltage starting methods are employed. Reduced voltage starting methods include, but are not limited to, electromechanical means like primary resistors, part windings, Y-start, and delta run starters, and solid-state means like soft starters and motor drives. All these methods serve to limit inrush current and limit mechanical stresses to the driven load. Today we'll discuss one of these methods, soft starters. Soft starters are astoundingly different from the primary resistor, part winding, and Y-start delta run reduced voltage starting methods we've previously discussed, because they are solid-state power electronics devices composed of no moving parts. Solid-state soft starters offer inherent advantages and come with their own peculiarities. Recall that the electromechanical means are all characterized by a clear and definite transition from start to run mode. For a primary resistor reduced voltage starter, either the primary resistors are in or not in the circuit. For a part winding reduced voltage starter, either part of the windings are connected to full voltage or all of them. For a Y-start delta run reduced voltage starter, either the motor is in Y configuration or delta configuration. There is no in-between stage, and the starter never makes a smooth, gradual transition from start to run. Really, the only time we ever saw an attempt to stage the transition between start and run mode is using a primary resistor reduced voltage starter with two banks of primary resistors. Even so, this is still a stepped approach, and the graph of inrush current would show noticeable disjoints during the transition periods. Doubly so for Y-start delta run reduced voltage starter, since this is an open transition method in which the motor windings are briefly de-energized between start and run mode. The open transition would be characterized by an undesirable transient spike. For this reason, soft starters are employed. A soft starter, among its many abilities, can smoothly ramp applied voltage from a predetermined start value to full voltage over a customizable period of time. This smooth voltage ramp yields more precise control of starting current and torque. Additionally, soft starters are often smaller, lighter, longer lasting, easier to adjust, and more efficient than their electromechanical equivalents. For the purposes of this lecture, we're going to largely ignore the solid-state components inside a soft starter that make these advantages possible and treat the soft starter as a box full of black magic. For those interested in delving into the dark arts, stay tuned, because later lectures on power electronics devices at the Big Bad Tech channel will go into nauseating detail about diodes, transistors, SCRs, triacs, and more. Long story short, it's complicated, and I want to keep this lecture manageable and concise. Most soft starters have the following user-adjustable characteristics: starting voltage, ramp-up time, and ramp-down time. More advanced soft starters may also include the following additional features: kickstart, current limited start, and constant acceleration. We'll briefly discuss each of these aspects. The starting voltage is ordinarily expressed as a percentage of full voltage. This is the starting voltage at which a soft starter initiates conduction to a motor. Ordinarily, soft starters should avoid going below around 40% of full voltage, since anything less may not produce the current necessary to even move the rotor. The ramp-up time is the period of time it takes for the soft starter to steplessly increase the voltage from the starting voltage to full voltage. The smooth, gradual nature of the applied voltage during the ramp-up time means there is no large current surge or sudden acceleration when the motor is first started. Additionally, some soft starters allow the ability to soft stop a motor, whereby applied voltage is not instantly removed from the motor, but rather steplessly ramped down to 0 volts over a period of time. The longer the ramp down time means the longer the deceleration period. Note, ramp up time is the positive going period from starting voltage to full voltage, and ramp down time is the negative going period from full voltage going down to 0 volts. Note the different start and end points. This is an excellent quiz question, and you'd look terribly stupid blowing something this easy. This particular graph shows the soft starter upon being enabled starts at 40% of full voltage upon receipt of an input signal. If this is a 120 volt line to neutral or 208 volt line to line light industrial 3-phase AC system, this would mean the starting voltage is 48 volts line to neutral and 83.2 volts line to line. This graph illustrates the soft starter would take 10 seconds to ramp up the applied voltage from 48 volts line to neutral, 83.2 volts line to line, to the full 120 volt line to neutral, 208 volt line to line upon receipt of the input signal. The graph illustrates the soft starter would take 10 seconds to ramp down the applied voltage from full voltage to 0 volts upon loss of the input signal. This particular soft starter has 3 adjustable potentiometers to respectively adjust ramp-up time from 0 to 20 seconds, start voltage from 0 to 100%, and ramp down time from 0 to 20 seconds. Again, note, ordinarily soft starters avoid going below around 40% of full voltage, since anything less may not produce the current necessary to even move the rotor. While we're taking a look at this particular soft starter, note the 2 indicator LEDs, ready and run. Since soft starters are solid-state devices, it's impossible to tell if they're enabled, unlike an electromechanical contactor or relay that physically moves when the coil is energized and is accompanied by a characteristic sound. It is for this reason soft starters often use indicator LEDs. The ready light remains illuminated when the device is powered up and ready for action. The ready light blinks upon being enabled and continues to blink during the ramp-up period. The ready light turns off and the run light comes on when full voltage is applied. Finally, during the ramp down time, the run light turns off and the ready light blinks until 0 volts. The ready light remains illuminated and the soft starter is ready to initiate another ramp-up event when enabled. These indicator LEDs are often invaluable troubleshooting resources. Advanced soft starters may also offer the ability to kickstart a driven load by allowing a brief initial boost of current at startup to break away loads with a large static inertia. This kickstart provides a current pulse for a selected period of time. The 2 remaining aspects of advanced soft starters, current limited start and constant acceleration, necessitate more involved circuitry in the form of a feedback mechanism. A current limited start sets a user adjustable limit to current during the ramp-up time. If during the course of the voltage ramp-up, the soft starter hits this upper current limit, it lets off the gas to keep current below the ceiling. This could be used to establish a predictable maximum current draw for variable applied loads at starting. Constant acceleration mode necessitates feedback from a tachometer, which if you'll remember from the mechanical power, torque, and speed lecture available at the Big Bad Tech channel, is a means of measuring rotational speed. The rotational speed transducer updates the soft starter with the speed of the rotor, and the soft starter can back off or step on the gas for the ramping voltage accordingly to keep acceleration inside a given range. This closed-loop control feature allows the soft starter to govern the physical output of a motor. Note this feature borders the traditional boundary between soft starters and motor drives. This begs the question, what is the difference between a soft starter and a motor drive? My answer to this question is simple. Soft starters govern the starting and sometimes stopping characteristics of motors, whereas motor drives govern the starting and stopping aspects as well as the running characteristics of motors. This is to suggest that most motor drives also have adjustable start voltages, ramp up, and ramp down times to govern the starting and stopping characteristics of motors. This lecture, therefore, serves as an introduction to motor drives. As we'll learn in later lectures, motor drives vary applied frequency and voltage during the run stage to govern the output speed and torque of the driven load using advanced closed and open loop control. Now that we've discussed in sufficiently general terms the features of a soft starter, let's discuss how they're commonly integrated into an electrically controlled system. Note this content is intended to be generally applicable to soft starters and does not delve into specifics about a particular soft starter. It is incumbent upon you to research the connections and specifications for your particular soft starter of interest. For the purposes of this lecture, we're going to assume a general purpose soft starter has 3 pilot level terminals, A1, A2, and IN, a 2-terminal normally open pilot level auxiliary contact from 1.3 to 1.4 for holding circuit purposes, and 3 2-terminal primary contacts, L1 to T1, L2 to T2, and L3 to T3. Some advanced soft starters may actually include integrated overload elements too. Note the term contact is kind of an anachronism, since these primary connections aren't physical electromechanical contacts that make and break connections, but rather solid-state devices that do or do not allow current flow based upon input conditions. Sometimes you'll see these devices inside the schematic symbol for a soft starter. By the way, there's a clue for the source of the black magic for those knowledgeable of triacs. Sometimes you'll see these devices on all 3, just 2, or only one of the primary legs, pending construction on the soft starter. Like I said previously, we'll delve into the dark arts of power electronics and semiconductor devices and circuits in much later lectures. First, soft starters, since they're solid-state devices, ordinarily need to be constantly powered up to run. Note this means that although they present notable advantages, a soft starter may constantly consume a small but measurable quantity of power, even when they're not actively being put to use. This also necessitates more wires, and with more wires come more problems. The pilot level ladder logic may indicate this power connection by placing the A1 to A2 terminals such that they ordinarily receive full pilot level voltage. Note the placement of the e-stop and overload contacts. When the e-stop and overload contact are in their normally closed state, the soft starter A1 and A2 terminals receive full pilot voltage and is powered up and ready for use. This is when the ready indicator light remains constantly lit. We'll discuss how placement of the e-stop and overload devices affect the functionality of the system during a ramp down or power off event in a moment. If you're tracking, you should probably already understand what it does. Note A1 and A2 are direct power connections, and IN is ordinarily the conditional input terminal. The IN terminal of the soft starter is the terminal which initiates closure or opening of the soft starter primary contacts, similar to a coil for an electromechanical contactor. When IN is energized by pilot level voltage, the associated primary and auxiliary contacts change states. Again, I'm using inappropriate anachronistic terms like open and close for this solid-state device. I should technically say it allows or disallows conduction, but old habits are hard to break. Regardless, the presence of the pilot level voltage at the IN terminal initiates the soft starter, and the absence of pilot level voltage at the IN terminal keeps it disabled. An operator enables the soft starter by closing the start push button. Note when the soft starter detects the presence of pilot voltage at the input terminal, the auxiliary holding contact closes, and an operator can now release the start push button. The soft starter remains in the enabled state. The soft starter, upon being enabled, initiates the voltage ramp-up event. Voltage at the T primary terminals goes to the predetermined start voltage value, and then seamlessly ramps up to full voltage over the predetermined ramp-up time period. Inrush current and the mechanical stresses to the driven load are thereby reduced in comparison to a full voltage starter. Additionally, in comparison to electromechanical reduced voltage starters, like primary resistors, part winding, and Y-start delta run methods, Inrush current doesn't experience a stepwise disjoint when the transition is made from start to run mode because it is smoothly ramped along. After the ramp-up period, the motor now experiences full voltage and runs at the rated speed and current. The system can now do one of two things: either keep the soft starter in the circuit or bypass it using a method similar to the run contactor in the primary resistor method. This implies soft starters can be divided into one of two categories. 1. Those soft starters that initiate the ramp-up event and then stay in the circuit. These soft starters are designed to carry full load primary current. The IC designates these start and run type of soft starters as having the AC53A utilization category. And 2, those soft starters that initiate the ramp-up event and then are bypassed during run mode and allowed to cool down. The IC designates these start-only type of soft starters as having the AC53B utilization category. For the purposes of this lecture, let's assume we're dealing with an AC53A rated soft starter designed to continually carry full load primary current. After we discuss timer relays, expect to revisit soft starters meant to be bypassed, making use of timers in later lectures. An operator wishing to stop the motor can press the stop button and remove pilot voltage from the input terminal. The auxiliary holding contact opens, and the soft starter can do one of two things. First, it can simply de-energize the motor and allow it to free spin to a halt by instantly dropping applied voltage to 0 volts. Or 2, it can initiate a ramp down event depending upon the user adjustable settings. If the ramp down event is selected, the voltage at the T terminals smoothly drops from full voltage to 0 volts over the predetermined ramp down time period. The soft stop, as this ramp down event is often called, basically keeps the motor energized with progressively decreasing voltage for a user adjustable time period after the stop button has been pressed, for the purposes of bringing the applied load to a smooth and controlled halt. Note the placement of the e-stop and overload contact, as currently implemented, do not necessarily serve to de-energize the input terminal, but rather depower the entire soft starter. Recall those soft starters allowing soft stops momentarily keep the motor energized after an operator presses stop. This isn't necessarily what you want to happen in an emergency. The e-stop therefore serves to not only remove the input signal to the soft starter just like a stop, but also entirely depower the whole soft starter. A completely depowered soft starter, even with the soft stop feature enabled, immediately disallows conduction through the primary terminals. Upon pressing the e-stop, the depowered soft starter therefore immediately de-energizes the motor. Similarly, upon sensing an overload condition, the open overload contact would serve to immediately depower the soft starter and immediately de-energize the motor. As I previously mentioned, advanced soft starters may feature integrated overload elements. In summary, a soft starter is a reduced voltage starter that seamlessly ramps up applied voltage from a user adjustable starting voltage over a user adjustable ramp up time. Additionally, soft starters can be used to progressively de-energize a motor for the purposes of a soft stop. A user adjustable ramp down time determines this period. Soft starters are not electromechanical in nature, but rather solid state. Due to this fundamental difference, one of the peculiarities of soft starter is their failure mode. Depending upon construction, solid state devices can sometimes fail in the conductive state rather than failing open. This means a faulted soft starter can act like a short between the L and T primary terminals and energize the motor even in the absence of an input signal. This is not exactly ideal. For this reason, soft starters may also include a manual or magnetically actuated electromechanical contactor in series with a soft starter expressly for the purposes of de-energizing the motor in the event of a soft starter faulted in the shorted condition. Here's a graph of line current for a regular electromechanical full voltage starter for a lightly loaded motor. The vertical scale is set to 5 amps per division, and the horizontal scale is set to 0.5 seconds per division. Notice the huge current draw, peaking out around 12-ish amps, upon being instantaneously and directly connected to full voltage. Additionally, note the motor accelerates briskly and reaches a stable current draw in maybe 1.25 or 1.5 divisions, meaning it took the motor less than a second to accelerate the applied load. This wouldn't be the method of choice for a fragile electrical distribution network or applied loads necessitating controlled acceleration. In contrast, consider the graph of line current for a soft starter used on the same lightly loaded motor. The vertical and horizontal scale are set to the same respective 5 amps per division and 0.5 seconds per division. Note the motor takes 3.5 to 4-ish divisions, or around 2 seconds, to accelerate the applied load. Additionally, note that current draw peaks out at only 9 amps. The soft starter therefore serves to limit inrush current demand and the mechanical stresses to the applied load. Here's both curves superimposed on one another so you can compare the two methods. The full voltage starter is in blue. It is characterized by a substantial inrush and a brief acceleration period. The soft starter is in yellow. It is characterized by less inrush current and longer acceleration. Alright, this about wraps up our introduction to soft starters. In conclusion, this lecture took a brief look at soft starters. We learned soft starters are solid-state devices used to reduce inrush current and modify acceleration and starting torque characteristics. Soft starters initiate conduction at a user-adjustable starting voltage and seamlessly increase to full voltage over a user-adjustable ramp-up time. Additionally, soft starters can be used to perform soft stops by progressively reducing applied voltage over a user-adjustable ramp-down time period. Advanced soft starters may include additional features. Soft starters present advantages because they are often lighter, smaller, and longer lasting than their electromechanical equivalents. However, must always be powered on and may fault in the shorted condition. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.